Okay. Good afternoon, everybody. We have a great speaker today, Professor Nadja Drabon from the Earth and Wider Science Department has down the hill from Observatory in College. It's great to have you here, Nadja. Got her college degree from Free University of Berlin, Germany, Nadja Drabon. Then she became a graduate student in Stanford on the West Coast here, across the. And then when she finished there in PhD, which were PhD, she went to the postdoc there, and then she get the postdoc here. And then 8 years ago, she's an assistant professor at the ETS department, and working from the very beginning on the primary Archean, which is to say the very deep history of time here on planet Earth. She's given to many those folk rocks related to the cycles of the cool sea. But what is important about her and her overall work is that it connects very much to what many of us here at CFA do, is taking one is because this is the time when the history of Earth went nears. Atmosphere and oceans, everything on the surface was almost nice the way it is now because life coming down is utopia. So basically, whatever effect you see in these overalls when some dramatic happens could inform what we might see or exploit. So very interesting for here. Got it? Look forward to this. Thank you.
Great. Thank you so much, Dupta. Can you all hear me okay? Great. So this talk is really a reflection of my long-standing interest in the habitability of the early Earth and how it was influenced by meteorite impacts. And you can maybe see like prominent name out there. I've been working on this together with Andy No, who I'm sure you all know really well, and with Don No, who was one of the early people who recognized the terrestrial meteorite impact record in the Archean. So on Earth today, there are about 200 impact craters preserved. Right? The smallest being smaller than a kilometer in size up to over 200 kilometers. So the biggest crater is the Third crater here, which is about 300 kilometers in diameter, and it's worth about 2 billion years ago. The most famous impact, of course, was the one that killed the dinosaurs, right? So that's the Chicxulub crater that is over here, that occurred about 65 million years ago. And again, was the trigger of the extinction of the dinosaurs. Of course, it's been long recognized that there was a major mass extinction event going on. People for a long time looked for the origin of what actually happened here, what caused this mass extinction, until at some point in the 80s, various scholars discovered an iridium anomaly associated with the boundary, indicating that it might have been a giant meteorite impact. So when you have an impact in your Earth, if there's an extinction associated with it, the extinction is not necessarily directly caused by the impact itself, by the environmental consequences. So in this case, we have about 10 kilometer diameter bolide hitting a carbonate platform. So that means we're releasing a lot of carbon and sulfate into the atmosphere. So forming sulfate aerosols, which are causing significant cooling. So 15 degrees Celsius or more of cooling in a really short time period. And then a little bit longer term warming by perhaps half a degree to 2 degrees Celsius on the CO2 that was into the atmosphere. Also, on top of that, we see evidence of the generation of acid rain, global wildfires, for tsunamis sweeping by, and all of those effects combined caused this big mass extinction. So more than 60% of Cretaceous species went extinct at this time period. But of course, there's also some other effects where you might actually see mass blooms and the aftermath of the impact of, opportunistic species, and potentially some sort of disaster turns out that radiated. And then we also have radiation of species. So I would always argue that, for us humans, this event was the best thing that could have happened, because without the nanodes that radiated, so we maybe wouldn't be here. So another big thing that happened associated with the KPG impact is a decline of the primary conductivity in the oceans. And we can see that here in the carbon isotope curve, which is relatively stable before the impact, and then we should see a sharp excursion towards lighter values, what happens is essentially, so you have got the water column. In the upper water column, you have a lot of ionic activity, which causes a carbon isotope gradient of the dissolved inorganic carbon. So when primary conductivity collapses, that carbon isotope gradient collapses with it, and that's what's causing this sharp decline here. So as you can see, it really depends. The effect on environmental life, they're really connected, and it depends in part on how big the bolide was, what the target was, what were the environmental conditions, and what was likely at that point, right? How complex was it? So taking us further back in time now, just for comparison. So an impact of this size of the KPG rock bolide, again, about 10 kilometers of diameter, today happens maybe once every 215 million years. And the Archean, these likely happen much more frequently, of course, or as you go further back in time, because just of the higher influx. So here's just the diagram by Simon Martiano of mass accreted in kilograms versus time for present. And of course, with first form, we have a lot of impacts, and that's certainly price. So I picked this diagram here because it's superimposing in blue here the actual terrestrial impact record that we have, just to compare. And one thing you're probably already seeing is that, for the late Archean here, the actual impact facts for which we have evidence seems to be higher than what the model is predicting, up to a magnitude. And I would still arguing that the actual terrestrial record is really the minimum amount of impacts, because the net layers are really easy to miss. And we have very few rocks that don't get here. So again, this is the minimum that we're seeing. So this is a complex table. The details don't really matter. But what you're seeing here is evidence for meteorite impacts in the Precambrian. And for the Archean itself, there's evidence for at least 16 impact deposits. So this table was published in 2012. So that's now 10 years ago. So there's at least 4 more impact deposits that we have found. How these are generally identified, most of them is by the presence of spheroids. So spheroids, as most of you probably know, is you have a bolide, and here we're talking about bolides 10 kilometers in diameter here, that are hitting Earth. They get vaporized, some of the target rock, they form a rock vapor cloud that then travels around the globe, and at some point condenses out. So you have got these tiny sand-sized silicate melt droplets that rain down on the Earth, and they form these spheroid layers. I actually brought an example because I'm a geologist, so I like to handle rocks. So here's one of the smaller impact layers from the Archean. You see it's just these small census grades that are fairly old. So there's something here that's associated with the iridium anomaly, an extraterrestrial chromium isotope signature, which makes us feel fairly confident that this is associated with an impact. Again, it's one of the smaller ones. In comparison, the KPG impact, the distal deposits are about 1 centimeter thick, right? So we are talking about substantially larger impacts.
So which one of the depots is on?
That's a spray.
That's the
One here.
Those spiral size or like the different pen size.
So given use the spiral size, but mostly the spiral bed thickness, as an estimate. All right. So now coming back to the beginning, where I was saying we are really interested, and I know a lot of you guys here too, and the influence of meteorite impacts on the habitability of planets. And a lot of work has been done on impact craters, right? So if a big impact, you create a crater, there's going to be a lot of hydrothermal activity going on. So you have hydrothermal vents, you might have geysers and all of that. You're increasing the porosity, permeability of your rock, you're restructuring it, and all of that provides, lots of temperature gradients and lots of interesting chemistry that is going on in these environments that could be really great for, prebiotic chemistry, but then also to potentially sustain life. All of that, so Zinsky published nice, just like summary of all of this. And he's saying, or he's recommending that impact craters should be considered prime sites for research for evidence of past life on Mars. And now that Dimitar has also done a lot of great work on this and has noted the possible importance of meteorite impacts for the habitability. Unfortunately, because, we're talking about Earth where a lot of the crust, 95% of the Archean crust has since been decided by tectonics. we don't actually have the craters themselves. So here, the proposed source crater, another one. So for all we know, we might be on the other side of the globe, from where these craters were. But it's still interesting for us to see, right? What is the influence of these giant impacts on that, more globally, right? When we see some kind of effects that are actually happening potentially on the other side of the Earth. So I'm highlighting here the sphere banks of Barberton, South Africa, and Barberton Queensland, because that's where I collect my rocks when I conducted the study. And one major reason is that the rocks are just really excellently preserved. So here you see a couple of spheres, published by Archean Eon in 2017 from the CT3 drill hole. And you see just beautiful preservation of the permanent crystal structures. You see diversification structures, you see photic textures. Again, in this sample, we have iridium anomalies, so everything's, really pointing towards it because it's just a heck deposit. So we have great preservation because the rocks only experience lower greenhouse grade metamorphism. So that's about 320 degrees Celsius. And then because a lot of the rocks were silicified really early on. So like all the pores and everything was filled with crystalline quartz. And that's going to really nicely lock in the signatures thing. And then the other reason why I chose Barberton is because there has been a lot of evidence on meteorite effects. So there are at least 8 meteorite impacts, or impact deposits that have been found. I know of at least 2 more that haven't been published on, but they're probably separate impact events. And all of these reflect bolides that are larger than about 20 kilometers in diameter. And we'll all just to kind of, angle here in time. So the Barberton Greenstone was deposited between 3.6 billion years ago and 3.2 billion years ago. And we have evidence for major impact about every 25 million years. I just want to emphasize again, this is the minimum. There might be a highlight and a lot more that you're missing. That's why, again, when you look at the sample, it just doesn't sense in that, we can easily miss.
We could lay a thing in 0 to 15 dollars. Isn't it that food or?
So that's the stratigraphic height. So it's not like a drill core that you're drilling down, but basically, so the rocks are deposited, like all those diameters, right? And then they're tectonically deformed. So now they're on the side. So we can actually just walk across this stratigraphy, which makes it easier for you.
I think a long way.
Would be great if we should do them more.
I assume CPL is for a little forward light. Type CPL is for a little forward light. I think that's my point. Do you know why they what are the features at its base the outer sort of the always was it some springs in your scope?
Well, so a lot of the features that we are seeing is vitrification features and just when you have like a melt that's cooling and right now just start nucleating on the sides of the crystal and then radiating upwards. So that's what we commonly see. Sometimes there seems to be some kind of like cores that might be like earlier material that was then captured by the more material. And some other places it's a little less clear and might actually have been some sort of acid.
Right. So I guess there is some vibrations.
Oh yeah, I think they have like also like the plate in there, which is causing some of the next colors, which just like just so I'm gonna be focusing in this talk on the S2 sphere of it. And partly because it's really widely distributed, so there's multiple sections we can analyze, and also because it's one of the larger impact deposits. So the bolide size estimates for S2 vary up to larger than 100 kilometers diameter. I think the most reasonable estimates is probably somewhere between 37 and 58 kilometers in diameter. So quite large in comparison to like KBG and that. So just visualize this, the system AGU something that Mom Sleep also worked on here, the Chicxulub bolide, so the APG bolide in comparison to the lower estimate of the S2 bolide size. Then you can look here at the crater size, it's almost 500 kilometers in diameter. So this was a huge thing that rained down. And that then, of course, begs the question, right? What was the effect on the surface environment? And in turn, can we deduce any effect on the early life, right? Was it disastrous for early life, or is there a possible way how it might have been beneficial for early life? So just to walk you through it, so I collected the samples, and the central part of the biosphere is about, so here's the inset. At two locations, that is the Brussels location and the Umba location. So the two locations are now, well, 10 kilometers apart. But as you can see, there's been a lot of tectonic deformation, and there's a major fault that is separating the two locations. So now they're 10 kilometers apart, they might have been too much further apart. The sediments are located in the uppermost Mendon Formation. So the Mendon Formation was deposited between 3.33 to about 3.26 billion years ago. And it's composed of at least or up to 5 cycles of ultraviolet volcanic activity. And those volcanic cycles are then paired by chert layers. So here I'm looking at the uppermost chert layer, and a unit that has been really extensively studied by Nadja Drabon. So what are the sediments we are looking for? We are looking at, right? So we want to look at what was before the impact to what's happening after the impact. So overall, the sediments are mostly composed of about centimeters of black and white banded chert and banded homogeneous chert. So chert just means microcrystalline silica. And so black and white banded chert, the white is just a pure chert layer, versus the black has some amount of organic matter in it, anywhere from like 0.1 to 2%. And so this is what it looks like. So I think anyone who's interested in early life, this is the type of rock where a lot of people look for evidence for early life. You can see nothing on the surface. It's just black. Yeah. So I already mentioned there's really quite a bit of organic matter. And some of it, like most of it is really involved with that it's hard to tell what the origin was. It's not that it's full of microfossils. But then in quite a few locations, we see beautiful three-dimensional laminations, as you can see here, really draping the topography at the seafloor, which shows evidence for cohesion when it was worked. And you see nice roll-up structures. All of that was really consistent with evidence that life was present in the seafloor there. Importantly, there's some evidence for differences in the water composition between the deeper water and the shallower water. So it looks like the deeper waters here where we can enrich the iron topaz, and in the shallower water that seems to have been a depletion of iron. And then lastly, and this is really important because when it comes to evidence for early life and carbonaceous matter, there's always the question, well, putting this as performed by Fischer Trojan, like the hydrothermal setting. Lizzie, who we extensively studied this unit, on no evidence for extrusive or amounts of polymetallic deposits that would indicate that really active hydrothermal fields here. So in terms of what can you picture what the environment might have been like, here's kind of my little cartoon for it. So again, you've got the water column, the lower water column that's enriched in iron 2+, the shallow water where they have another iron 2+. There was certainly evidence for life, but with the Archean, we have to recognize that productivity was probably much lower than it is today. We do think there was life present, but just probably not as prolific there as today. So the two sections that I'm looking at, the the Brussels section, both with a positive impact this chemokine. So they show very little iron for the impact event. And it seems that within this environment, the Umba section was relatively shallow compared to the Brussels section. So let me show you in detail the two sections that I worked on and kind of the sedimentology and the hydrography of what the Gordon here. So here we've got the two sections. I measured 5 meters below and as high as I could get above, so up to 10 meters above the impact event. And so here is the S2 impact event. So this is the first occurrence of spherules. And this is also the unit that developed iridium anomalies, have found iridium anomalies, and then the beryllium isotope. So at the base, again, you're depositing from base to top. Below the impact event, we have useful black and white banded chart. In the Brussels section, we can see there's some evidence for current energy. So here, this is a Sandia component from below the impact where we see beautiful cross laminations. So there's some, low energy currents gently sweeping across the ocean floor here. And then when we look at thin sections here, we can see quite a few thin sections that there's mention of siliciclastic detritus. So that means we are somewhere relatively close to some of the coastline with this material was eroded and then deposited. In contrast, the Uma section seems to be overall lower energy. So in the foot sections, we see a lot of these beautiful fine combinations of animations, some really thick, broken up and rolled up in some places. If there's a stochastic detritus, it's intraclass, and anything higher current energy tends to show as these like churn plate conglomerates, and those have been interpreted for skull deposits. So essentially, here we are at the back fairweather wave phase, the shallow water, and here the low fairweather wave phase at the pastoral wave phase and slightly water. So then, of course, we have the impact event. So as to here, in both sections, we see really coarse clastic sands or conglomerates. So we see associated with the spheroids a high energy event that essentially behave like a storage. So you can see essentially here, it's like really phosphate and erosive at the base and then gradually finds upwards. So then there's like a storage. And this is oftentimes, so we do see this associated with any single impact, not only environmental, but also just everywhere in the Archean. And this is generally interpreted as a tsunami event. So you've got this high energy currents coming through, sweeping up the seafloor, rolling into it, and then settling out. Above the sandstone layers that the participants experience, we have this about 1 meter thick layer of black chert. So this is organic rich chert. You can see it over here. That is still really beautifully normally graded. So what we think is happening here is that the tsunami once by rips up the seafloor, and a lot of the refined organic matter that was at the seafloor is going to go into the water column. It's going to be suspended and slowly rain out. And that's what you're seeing here. So it's still associated, it's still the same event that is forming these two sides from biosphere. So then in the boosted subsection, we see actually another thick sandstone layer and then potentially a third. Both of those still contain scales, and at least the lower one here is clearly nicely normally graded. You can see a thin section, so this is the top of the photic layer. Then we have got this somewhat erosive surface, and then the sandstone that's full of these variable particles. So what is possible, what might have happened here is that you have the tsunami sweeping by. Sorry.
That was such how thick and fall out later than have been towards the breastplates and subsequently.
Oh, not real. I think it might have been because it is going to be compressed somewhat. Maybe double the thickness, if I have to guess.
Not that one.
I don't know because yeah. So we see these multiple thick sandstones. So what might have happened is that usually a tsunami is going to not be just one wave, right? It's a wave train. So then in shallow water, maybe you have another big wave hitting the coast and generating another one of these thick sandstone beds, or it could be that the tsunami was somewhere and then coming back. I should mention that the highest balance of spheroids is actually up here in the third sandstone bed. All right, so this is the general stratigraphy associated with the impact, but let's go and make so much of this area here, because this is where we see something really curious occurring. And that is we start seeing this beautiful euhedral crystallites. So you can see beautifully shaped crystals here on all the sediment. It looks like there might be two types of crystallites, like one that is like in the top of the column layer, and one so here's an erosional uniformity, and then we've got some more. And it looks like there's two types of crystallites, but it's really hard to tell what they originally were because everything's been replaced. So everything is now silica. It looks like whatever is filling, what is filling is now it's the same material that fills any kind of like fractures or vein. So we know it's not the primary material. So what could it be, and what might be the significance of this? So for that, I took a little bit of a closer look. So when I look at I call these just type 2 pseudomorphs that are in the top of the funnel there. What you can see here is just the size of the pseudomorphs. We can see that they're relatively large compared to the largest plastic ring. So they're not at hydrodynamic equilibrium. And then the crystallites above, they are about the same size, maybe a little bit by that. Then we can look at the crystal habit. Again, like a lot of these beautiful, like hexagonal features, which indicate that there was either no sedimentary transport or very minimal, because otherwise you would see evaporation. And also what is interesting is that there's, differences in the most common crystal habits between the two types, indicating that they're making two different origins. And then lastly, we can look at the crystal orientation here, and you can see that the crystals within the polar layer here are really remnantly oriented. So that means they're likely not transported by currents, or they didn't settle out of the water corner, versus the crystals above, they're nicely oriented, so indicate that they either settle out of the water column or again were transported by some really minor currents. So what would this be? It's still a little bit hard to tell. I think the two hexagonal minerals that are possible include apatite and tourmaline, but I don't think those are options, simply because we do find primary apatite and tourmaline in these sections. So they don't seem to be replaced. And in terms of the crystal habit, the most likely candidates are aragonite or naphthalite. So what does this mean? So we've got these unusual crystals happening essentially immediately in the aftermath of the impact. And that's with some really interesting modeling done about 10 years ago. So it'd be great if someone here could, do some more modeling with more sophisticated approaches. What they were finding, they were looking at the temperature effect of these impacts and how that might have affected, ocean evaporation. So for an impact about the size of S2, maybe on the larger end, you can of course see like really intense atmospheric heating from thermal radiation. And that in turn might cause the evaporation of ocean water, so to several tens of meters. We see also in the geological record associated with two other impact events in the Barberton area, evidence for ocean evaporation. So here, immediately above the event, we see these precipitative crusts that are also brought to form from partial ocean evaporation. So the hypothesis that we are working on right now is that these might represent evaporites. So you might have evaporites here that formed randomly oriented interstitially, so within the sediment. And then you've got these other crystallites, which seem to have a different origin, that might have formed the uppermost water column, right? That's where the evaporation was the highest, and where you might nucleate some small crystals that then settle down. It's something that we see in like normal salt pools or whatever, and I believe they're called grapes from heaven, which sounds very nice thinking about how the disastrous this is. So to really test this hypothesis, we need to get a much better estimate of the crystal angles. We can't do that from thin section, so I hope to do serial grinding, where you just take a photo, polish, and then go all the way through your sample, and then you can reconstruct and see how measures the crystal happened. All right, so moving on. We've made it through the impact. So what's happening after, right? What are some of the possible environmental events? And the first thing that we noticed in the silt section, even in outcrop, is that we started getting a lot of iron-bearing minerals coming up. So especially above the sedimentary layer, we start having these grains here that are composed of really minute, incredibly fine, like submicron hematite grains, some magnetite, siderite, stognomeline. And then as we go higher up, we start seeing an increasing abundance of siderite, so currently a carbonate. In the lower section, it looks a little bit different. So above the formal layer here, we start seeing a lot of siliciclastics coming in. And it looks, when you just look at the start section, it looks like we are going back to normal, but it's not, because before we didn't really have siliciclastics. All of a sudden we see them coming in. So here's a nice fine structure of sandstone. And then above them, that's when we get into these iron-bearing charts that are full of siderite. All right, so this is just the sedimentology and petrography of the two sections. Let's look a little bit more at the geochemistry. So firstly, I'm showing you aluminum here. So aluminum for us is a proxy for just how much siliciclastic sediment is coming, how many Ks. You can see the two sections show differences. So here we've got the average 2.7 plus minus 1.5% versus 0.7%. And this is really in agreement with the sedimentological interpretation that this is shallow water. You are closer to your sediment source to the exposed land compared to here. So what's happening after? And the booster slow section, that doesn't seem to be here notable change that is significant at all. The only thing I would highlight here is that, we have much thicker sandstone beds than we had before. In the Umma section, however, we do see a clear change. We see much higher plastic sediment input that then goes back to normal and also go into this iron-giving charts. So overall, what we see, especially in the Umma section, that really impact is a temporary increase in plastic sediments. Associated with that, and really importantly, we can look at the phosphorus. So the phosphorus is to some extent correlating with the just sediment input. So we see that really in the Umma section. But what I think is almost more important is that there's an increase in phosphorus with the spherules themselves. So you can see here in both sections, the sphere beds have really the highest phosphorus content. But really, it's just almost outrageous how high it gets in the two sphere beds in the cell section. And that topmost sandstone that I mentioned earlier that has the highest percentage of spherules. So here we have a phosphorus content of 1,300 parts per million, which is almost 20 times higher than the background. So from the impact, potentially for bolide vaporization, and then added to that increase in sediment influx, we might see an increase in nutrients coming in for it.
So is this connected level like phosphorus?
So in terms of the sediment influx, you do see quite a bit of the appetite coming in. That the spherules, I'm not exactly sure the phosphorus is. So it seems to be associated with the balance of spherules that we haven't done to that understood. So next, let's look at the balance of iron. So iron in both sections poorly impacts relatively low, about 0.5%, which is really consistent with being above that chemokine that I mentioned earlier. So when with the impact in the interstitial section, you see an immediate increase in iron that actually peaks above the second sandstone belt and then gradually returns back to normal. So I'm not showing any samples here, but I've got some shale samples from laterally that show really return back to normal. So there's an unusual increase in iron in these sections. Immediately with the impact in the interstitial section, and then in the Umma section, it seems like the increase in iron is really starting to happen once there's increase in sediment and fats receipts. So this increase in iron is really interesting because iron could be a potential, or could potentially be really important for the biosphere, right, for iron cycling. So I first want to think about a little bit where is this coming from, if it's associated with the effect, and then I'm going to talk a little bit how this might relate to early life. So where's the increase in iron coming from, right? There's several different possibilities of what's going on. So we could just have gradual deepening, whether related to the impact or just backward deepening, right? We're deepening, we're passing through the chemokine to deeper layers. It's been proposed that the impact triggered really extensive uplift and erosion of mafic crust. So mafic crust is one transition out. It's possible that the impact triggered mafic, volcanic, and or hydrothermal activity, which I think it's like undoubtedly that this impacts create hydrothermal activity, at least close to the craters. So could this be something more global as the question here? And then lastly, it's been proposed that the increase of iron could be related to ocean mixing. Right, so you're with a tsunami, you're stirring up the water column, bringing high water, deep water into the shallow water environment. So first, do we see any evidence for deepening? So in terms of sedimentary structures, there's really no clear evidence for change in sedimentary environment. So when we look at the interstitial section, we still see beautiful cross-bedding here, which indicates active currents. So there's no clear evidence for deepening there. And similarly, when we just constantly look at the grade size, you don't see any change. You don't suddenly see little currents or turbidines and really super deep water sediments. So there's just no clear evidence that we are deepening. So I think we can make it as split as possible. Next, we can look at the possible change in hydrothermal activity. So people look at that in terms of the European anomaly here. And before the impact, we have somewhat similar values, about 1.5, which is a signature that is higher than today. So today's ocean is looking around 0, around 1. So it's higher compared to today, but this is just in general the signature of the Archean oceans. There was a high effect on the mantle, so general hydrothermal activity. Whatever sediments you're looking at in the Archean, they're going to carry this, slightly higher hydrothermal signature. So after the impact, there's no really statistically significant change that we'll see. So again, I don't doubt that it can cause hypothermic activity, especially close to the crater. But on a more global scale, in this case, following on maybe on the other side of the globe, we don't see that like nearly to the sediment stream. And then again, the question is there any increase in mafic rock, whether from increase in from uplift and erosion of mafic rock or increase in mafic volcanic activity? So for that, we look at the chromium over zirconium ratio. So chromium is going to be enriched in more mafic rocks and zirconium in more felsic rocks. So the more mafic something is, the higher the value should be. And again, we don't see any statistically relevant change here. If anything, there might be a change to slightly lower values here, which will indicate a slightly more felsic provenance. So all in all, I would argue that the decrease in iron is most likely coming from the mixing of the water column, which is bringing this iron-enriched deep water into the shallow water environment. So just to summarize the first part of the talk, right? What can we say from the geology of these rocks? Well, what is the environmental effect of this to meteorite impact depth? So firstly, we see very clear evidence for tsunamis sweeping by. On top of that, we have some potential evidence for partial ocean evaporation. So we're not evaporating the entire ocean, it's just the upper few meters to tens of meters. And that's what we are seeing here in these crystallines that are forming in the water column in the segment. There's an increase in weathering and erosion. So that's a part coming from the tsunami coming in, but also likely because if you're heating up the atmosphere so much, you're going to increase silicate weathering. So that's going to increase the cellular lot. And then, of course, we see an increase in iron in shallow water environments. So, that's happening. Is there any measurable effect on life that we can see on these rocks? So first, for that, of course, we look at the organic matter, at the carbonaceous material, and we look at carbon isotopes, right? Because life prefers the lighter carbon isotopes and the heavier ones. So different pathways here, I want to have relatively light carbon isotopic signatures. So when we look at our analysis here of the magnetic formation in general, we see values between about -27 down to -39, which is very much consistent with life, right? There could be a Calvin cycle or the Youngdahl cycle. It's really hard to tell, because of course we don't have microfossils. So I mentioned earlier, right? Organic matter, a lot of it is in the solar plants on the simulations. But I haven't found any nice microfossils in study in this case. So carbon isotopes are less bad. So what does the data look like? And the data first started coming in, I was a little concerned. There's a lot of scattered here in both sections really. It's very hard to see any type of return. However, this is really typical for key insurance that we see with some of the variability. And it's really hard to pinpoint an exact reason for why that's happening. There's many different possibilities. But what is often cited is that you're really in a oscillatory environment. So you might have some amount of primary productivity and then just another secondary recycling. So fermenting, respiring organisms or oxidizing because the values get pretty low, given like design, methylogenesis, and methylotropism going on. All right, so this is kind of the background of we are dealing with. So what's happening after the end? So first, let's look at the color layer. So what you're clearly seeing here is a shift to much more homogeneous values. It's very interesting. The way we are interpreting that in part is that we have the tsunami sweeping by. It's clearly ripping up the floor. I mean, you can see the evidence right here. And what's happening in the water column is that if you bring all this organic matter, so from life that was maybe happening in the water column, but also debris from the seafloor, you're really mixing it up and homogenizing it, and that's going to rain out. And that's what we're seeing in might be seeing here. And then above the impact, you're like, there, we again start seeing kind of scattering a lot of back and forth, but here almost starts looking bimodal. Versus in the Umba section, we maybe see a shift towards slightly heavier values that are, again, just a little more consistent.
The homogenization is happening in the initial seeking, which are the rated average of the previous layers.
I mean, ideally, yes, right? This is just a snapshot of our location, so we don't know, right? It depends on what was right in the ocean floor, how deep is it eroding. So it's not necessarily the average of all of this. automatically it's eroding. Plus, you might be having stuff coming in from further away, right? And from like the tsunami washes over the exposed land and the stuff that's bringing back in. So in theory, yes, but I don't think that we are like capturing that to be somewhat here.
Of course, I'm struggling. Like, this measure is like how wide or
Oh yeah, it's 0.2 per number. So then we're very good. All right. So before I start interpreting this, we're looking at really old lots. We need to think about post-transitional alteration, right? So you might have the effect of metamorphism here, which is causing thermal cracking, which might refer to remove the lighter carbon. However, this is something that should happen to all of the rows together. But here we see this beautiful stratigraphic dependence of the carbon acetone signature, which makes me think that this is not significantly in here. And because also we are at such low metamorphic rate, the effect that we would expect would be no more than 3 kmol. And as you can see here, right, that you see some really narrow clustering, like if you go, you might have something, preserved from what is originally deposited. There's always the trouble with carbon migration. So charts, whoever has looked at the sample, it's a really rigid sediment. So if there's any type of tectonic stress, it tends to fracture really easily, and that will allow some kind of fluid flow. And typically what we see these fractures is just more chart, just a different fracture. We have 150 thin sections throughout both sections that have evolved closely. I found one single fracture flow right at the bottom, maybe saw a tiny bit of a red there. So I think that was really minimal carbon migration. And I also again want to emphasize that some of these fine carbonaceous structures, so these laminations are really at the micron scale that we have there. And then lastly, there's of course the issue with equilibration with carbonates, because again, we do start seeing sodides in here. But this is something that people usually worry about at much higher temperatures. And when I look at the organic carbon isotopic signature versus the carbon at 8%, you don't see any clear correlation. So that's making me feel much better about here. So now going to, some of the questions I was posing at the beginning is, do you find any evidence for a negative effect on the biosphere? Right? I was talking about partial ocean evaporation, what tsunamis making by letting darkness more of the dust in the atmosphere. This would really likely have an effect, especially on photosynthesizing organisms, right? Because need light, then the shallow water column. So they might not like that in the time. So at the KPG boundary, what people see and what they use as evidence for collapse of primary conductivity is a negative shift in the carbon isotopes. And if you haven't here, you might be able to see that in our sections. And there's just in the follow layer here, there's potentially a linear negative trend. So here, there's moderate correlation rate. So this is about half a panel. You might have to have another view or maybe a third. And then you see a really minor shift potentially, but here it's about 2 panel. So could this be evidence for collapse of primary productivity? I would argue that it's very likely not. And this is kind of going back again to what I was saying, at the KPG boundary, what we are really seeing, what you're capturing is the collapse of a carbon isotope gradient within the water column. But because in the Archean, the PCO2 was so much higher, that means the dissolved organic carbon in the oceans was much, much higher. And at the same time, the conductivity of the biosphere was much lower. So it's much less likely that there was actually a carbon isotopic gradient in the water column. So what I think is more likely is that we are looking at size segregation of different organic particles. So here again, the carbon isotopes in black, and then the maximum grade size siliciclastic materials, so not organic but siliciclastic. I mentioned to you, both sections show really beautiful novel grading. And that correlates more or less with what we see in terms of the carbon isotope signatures. So it could be that some of the larger particles have maybe a slightly heavier carbon isotopic signature than the finer ones, which is sometimes that in the model you sometimes see that different particles, even if they're sort of amorphous, carry different isotopic signatures. It could also be at the same time, right, that, you're mixing up the ocean floor or the organic matter that rains out, and then maybe the biosphere is actually taking right back in. So you might also see some mixing the copper, organic matter production by the biosphere. So no clear evidence for negative effect. You can also maybe look at the total organic carbon abundance here in weight percent. We can see that there's, compared to the background, which is maybe like 1, maybe a little bit higher values. But TOC, increase in TOC could have many different reasons. Again, it might be just the ripping up of the seafloor. And also I would argue that these higher TOC values are not unusual, right? There's nothing like unusual about what we are seeing here. So overall, I would say, in my mind, there's no question that these impacts on the short term have a negative effect. I think it was just so short term that in the work record, people have a really, really hard time figuring out. So I think what we need to do is much finer scale analysis, maybe at the medium scale, and even then we might now be finding it. And I just want to cite something that Andy Noel likes to say, that at this time, life was very simple. We have bacteria like here. So when you imagine in the morning, when you brush your teeth and you kill 99.9% of bacteria, by the evening they're all dead, right? So the conditions like that for a few years, for a few years, won't get better, by a few might just wipe back them down. So let's shift gears a little bit and think about possible positive effects on the biosphere. So here I'm really thinking about the increase in phosphorus and also the increase in iron, right? Because those two might have a really important contribution to the biosphere. And I think especially the iron is really interesting because it's, the uppermost water column was depleted in iron, and it might really act as an important metabolic agent that might have been utilized by the biosphere. So just like talk you guys through some evidence that there might have been some iron cycling by the biosphere in the aftermath of impact. I'm going to color code the carbon isotope. So here, it's just again aluminum versus zirconium, showing nicely that that the variation that we see here relates to the sediment input, so like either the triidal material or the organic matter that's coming in. And then so I'm using aluminum sediment input and then also iron, just to see how much iron are we looking at. Do we see any shift with the increase in iron in our carbon isotopic signatures? So these lines here is about 1.58%, and I just chose it arbitrarily, but I just thought that I nicely divided our data. But it did turn out to show some really interesting distinctions between our carbon isotopic data. So here again, that's the carbon isotope data that I showed you earlier. So, and here, these bold spots is where we did get geochemical data for some of the analysis. And the thing that probably pops out to you is that, in the UMA section, when we start doing more homogeneous layers and slightly heavier, we see really iron-rich strips that have low trial input. And similarly, in the booster sill section, right, lots of variability before iron comes in, and the samples that are high in iron but low in the trials show this really consistent and relatively heavy isotopic signature. The way I interpret this is that these samples over here, they're higher in aluminum. That means there's a lot of other reworked sediment in it, including subwater organic matter, right? That was laying for, million years or a few thousands, hundreds of thousands of years before. So these samples are, so to say, like contaminated by the trials. So it's clear that there's some kind of connection between the carbon isotopes, so the carbon cycle, and the increase in iron. Here's just a different way of showing that in response plots, just showing that there's so much less variability in those like high iron low trial samples and how they're relatively heavy. So it's our first piece of evidence that maybe something's happening with life because of the increase of iron. The second thing that is interesting to look at is that these samples petrographically, of course, different, and that's because they're really full of different iron-bearing bases. So that includes some hematite, magnetite, and still nomalate, but really predominantly they're full of siderite. So siderite again is an iron carbonate. And when we look at the thin sections here, there's some evidence that the siderite is diagenetic in origin, so it doesn't look like siderite that formed in the water column and then settled out. But the siderite seems to have formed within the sediment itself. So we never see siderite being reworked in nice sedimentary beds or short grading or apparent structures. But instead, what we often see is what we always see that siderite is associated with organic matter. And oftentimes we see really clear spatial associations. So this dark cloudy material here is organic matter, and you can see it's just like root and covered with siluric grains. And then, as I mentioned, you also see iron 3 plus mineral, so hematite, for example, really, really fine. So if you can see this as a microcosm image, this is a 2 micron scale. So a lot of these hematites are sub-micron in scale. And again, they're really closely associated with organic matter, so that's this dark cloudy stuff, micron. And then in this case, you see these dehydration cracks here that are then filled with silicate. So there seems to be some association between organic matter and these iron minerals, and especially silicate. So the last thing we can look at is the carbon isotopic signature of the carbonate itself, because that can tell you something about where's this carbon coming from, right? What is it taking up? Overall, the data looks like it's fairly light and variable at a very small scale. Like, so this is between about -2 and -8 per mole. So that means that the carbon source that you're looking at was depleted, or has a depleted carbon isotopic signature. This is coming with a really big caveat, and that is to like really fully understand this, we need to know what the carbon isotopic signature of the result of organic carbon was, which we don't have a good handle on. So for that, we would want to look at like calcite, or then dolomite, like one shallow water environment. But these are really fun few between and Archean. This, in general, it seems to be relatively stable for the Archean at about 0 mineral or slightly tinier. Reisenau and 1989 actually published data for the same area, but just about 30 million years younger. They also had a value of 0. But it's hard to tell what the exact background is. So anyone knows, like shallow water carbonates at 3/16, please let me know. But yeah, so overall, putting all of this together, this different lines of evidence, could this be an indication of iron cycling by microbes? So I would like to propose that what we are seeing here is very much consistent with microbial iron cycling. So what's happening here is that you have iron 2 plus available now in the shallow water column from the ocean mixing, and this one that kicks out a photophytotroph. So I was mentioning earlier, right, there was likely low productivity, the oceans were low oxidants, especially in the shallow water. So once you have iron 2 plus available, this is metabolically much more favorable, like carries much more energy with it compared to, for example, thermogenesis and thermotrophy. So the influx of iron 2 plus in the photic zone might have triggered photophytotrophy. This then would create fireball electron sites that isn't soluble, so it would set out solid particles. So this is all we might be seeing with the tiny hematite that you're looking at. And then we might be looking at dissimilarity ion reduction, right? Where we use an electron from the organic matter, combined with the iron, to release iron 2 plus back into the water column. This together with the CO2, or this process in general is a really strong alkalinity pump that triggers iron carbonates, the siderite formation. This has been nicely shown in experiments. So a lot of the siderites there show these nice round shades. And this is what I see at some of my samples that are the best preserved. It's like 3 to 4 micron sized, like round siderite lines. So some of the iron 2 plus might go into siderite, or maybe if a lot of silica comes into greenolite, and then other will be returned into the water column. So overall, I would say that each of these different lines of evidence here, if you look at them individually, it's been in 2 different ways. But putting all of this together, I think it's quite possible that the recent iron had an effect on the biosphere, and in particular, might have really triggered, iron cycling. Yeah, so coming back to my question, right, where there may be additional effects of meteorite impacts on the alkali, I would argue that with this I2 plus, acted as a potential electron donor in the photic zone. And at the same time, we've got the enhanced weathering. So increase of phosphorus that way, and then bolide vaporization, which causes an injection of nutrients where the Archean are generally, in the Archean, the oceans are generally regarded as nutrient depleted. So it might be that at least for some time period, there might have been some transient benefits to the biosphere. Of course, this wouldn't last forever. It's hard to say, what the time scales are and the rocks that I'm looking at here. But eventually, right, things will go out to steady state. So just to summarize, because I'm at the end of my junk here, we see evidence of several environmental impacts of the S2 impact, right? We see evidence for tsunami, partial ocean evaporation. There's really likely there's only some period of darkness, an increase in northern erosion, and an increase of iron in the shallow water environments. And this in turn, certainly had some really short-lived detrimental effect, especially to photosynthesizing organisms or metabolisms. Where I would say that, pure water troughs might have just not cared as much. And then in the medium term, there might have actually also been blue or iron-based metabolisms due to the influx of iron to health and meteorites. And that's the end of my talk. So thank you so much.
From now, every time I brush my teeth, I will text everything. Questions? So can I ask a question? I think that's sort of toothbrushing brain. How long do you think the fire takes to sink in the ocean? How and go back down from D to E, I guess.
Oh, like going from the
and so if the organisms are responding immediately, but how long does that move?
Again, it's really hard to say. I wish we had better ability so I could actually date the rocks that I'm looking at to see when is the iron going away again. Your walls are too big. My best guess, and just from talking to Andy, would be maybe through tens of thousands of years. Right, there's going to be some cycle. You have the soluble iron 2 plus, then it comes insoluble, sinks down, then 2 plus is released again. But eventually, it's going to use up the iron 2 plus, and then at the same time with the phosphorus, so phosphorus tends to absorb onto iron 3 plus particles, so that might be also something that is kind of limiting the length of time there is ever.
Yeah, so it's not just the physical process of itself; it's also the cycle.
Yeah, it's also on the cycle. Yeah.
Okay. Yes, thanks.
I just want to go back to the beginning and ask a very simple question. So let's say you get your sample. Apparently it goes down 40 or 50 feet or meters and 1 centimeter across, or just saying the samples that you show.
So just imagine, so initially when sediment is being deposited, you're always going to cover as a layer cake, right? All the sediments at the base, the new sediments on top, right? And then it's all tectonically deformed, so everything is not like this. So actually, if I can just walk over the rocks, and it's a big outcrop. I would say it's the size, a little smaller than this room, perhaps. And then I could just go with a hammer and just walk along that sidewalk.
So it rotates. Why does it rotate? You're saying
just because of tectonics. So the rocks are really all over, right? They're 360 years.
So do they all rotate? I mean, I was in Iceland yesterday, and we're the North Atlantic plate and the European plate, and they're moving apart horizontally. They're not running upside down.
Yeah, some do near faulting. Yeah, it's just something with the tectonic forces of our planets that allows them to rotate out. Because when you think about holding facets, right? You see it's traveling holding up and down. So that's kind of what happened here. And it's really to our advantage because again, I don't need to just walk across and walk through this area.
So for other impact craters, do you see a similar lithographic the trends that we see here, suggesting that this would be a cycle that they reflect through many times?
So this is exactly what I want to do next. So there's some potential indications. I have a grad student who's working on the S1 sphere net in Australia. But the S1 sphere net there, we also see an increase in iron. It's recorded from the S3 sphere net as well. So yeah, that's kind of the goal to look at S2 a little more broadly. So there's potentially new discovery of the S2 sphere net in Australia. So just saying, okay, you're on another crater. Do you see the same response, or is this something local? Right, that's a big question. Is it something local or global? And is it something that will happen every time in the European that you have a big impact, or is it something that just at that time period that the environmental conditions are just right that you see them as a, so it's a good question.
Great talk. I was wondering if you wanted to the direct photo observation of items or anything. So for this diagram, we have microbility of use oxidation and reduction by dynamics. But there's also your UV light equals observation of ferrous iron zero iron tree. And that would all be sort of the impacted by now being back because there will be some.
Yeah. Yeah, I think it's something we need to consider. Yeah, it's pretty right. I think in the medium of the macro impact might be done, some might be less likely. And that's again a very short time period, up to maybe 3 years. So after it's actually possible. I think in terms of fluxes, if it's biosphere versus observational biosphere are looking dominant, different was which I think we see some of that's odd. But then you still have, the deposition, but then the similarity and those genetic origin from potentially to similar and reduction. So you need a way to explain that, and I think the best way to do that is with your kind of
Right. And the other short question was in the crystals that you observed in the example ones, there were different shapes. Are they compositional there?
Yeah, so again, everything's been replaced. So unfortunately, yes, I don't think that necessarily means anything for the original composition. And yeah, again, I think my best guess right now is aragonite or nactonite. So really what we need to do is like detail 3-dimensional imaging to be the
two small things. How uncertain is the amount of ocean is on there at time? This is after the water that builds up as that's about up and down as that affects any here.
So at this point in time, fairly certain that they consistently had an ocean. We see, these sedimentologists, any type of sedimentary rock, almost sedimentary rocks that I see in South Africa, in Australia, in India, very positive in water. So we do see that it's a water sure.
The other thing is, so if there's evidence for, or not evidence for blooming, we talked about that you passed this picture was currently, then that opened up the evolutionary process was pretty different species and different ways. So is that one of your goals is to just this is before multicellular life, right? So
Yeah.
if it's one of your goals is to look to some way see if there's been a tremendous change in character of life itself.
I would love to do that. I think in terms of, because the rocks are so they have experience, the which is great metamorphism, at least with the tools to be able to back the time right now. I don't think we can narrow it down as much. I don't wish we could. So hopefully some of the work that people are doing with like with specific carbon isotopes of different molecular structures, maybe that's something that's get it. So just ensure that I would love to do it. I know that the ability is not to go to the city. I know that the progress to it.
And last question, that would be last, because I'm sure you'll. You mentioned microcosmos. And so, what are the oldest microcosmos? So it's that bulk thing.
So microfossils are really disputed. There's also the video the shows. That, the opinions really very shallow. And I think in general, the views are not favorable right now. So people have looked for microfossils in the Marlton sequence, including, and, found like a few that could be microfossils. But to find like one concession with microfossils, we have to have 300 concessions to find one. So unfortunately, it's not reasonable evidence. So.
Well, that's fine. And this is right. I guess what this about the zone, this is like the next. And I think this is